This is Pre-Calculus Math Analysis, Section 7.4. This is going to be part 3 of the notes. Last time we talked about denominators with multiplicity. That's where we left off. There is a third type of problem, and that's going to be a denominator with prime factors, which means you will not be able to split up the bottom. If the denominator has a prime factor, then we need to include a linear expression in x. In the partial fraction numerator. I'll put numerators because this is going to be a decomposition. Here's an example. Let's say I had 3x plus 4 over the quantity x squared plus 2 squared. Well, normally, if I didn't have that x squared inside of it, then I could write a over x plus 2 plus b over x plus 2 quantity squared. Okay, because x plus 2 is a linear expression. The problem is, when we get that squared in there, this is now a quadratic. It's a quadratic that we can't factor. So our numerators are no longer constants. We have to make them linear. So we're always sort of trying to go one power down with the numerator. And that's going to change our numerator to ax plus b. And that right there is our linear expression in x. And then we need, because of the multiplicity in this particular example, we need another linear expression, so I would just use different letters. Cx plus d. Okay, and that's how we're going to have to solve the problem. Without further ado, example 4, prime factors in the denominator. Write the partial fraction decomposition of the expression negative 2x squared divided by x to the fourth plus 4x squared plus 4. All right, it's not an improper fraction, so that's good. That means I have to ask myself, can I factor out the bottom? And it does turn out you can here. This can be written as negative 2x squared divided by x squared plus 2, quantity squared. Okay, that looks like a quadratic factor on the bottom. It's not a linear factor. Also, it does not factor, so therefore it's prime. So I have to write ax plus b over x squared plus 2 plus cx plus d over x squared plus 2 quantity squared. Now our next step is to use common denominators and somehow form a system of equations. The bottom one here should be multiplied by another x squared plus 2 on the top and bottom. This can stay the same. So ax plus b multiplied by x squared plus 2. I have to FOIL that. The next one, cx plus d, well, I don't have to multiply this by anything, so it's really kind of just like multiplying it by 1. And that's going to be the same exact thing. Now I have to put those two things together and equal it to the numerator. Negative 2x squared should be equal to ax to the third plus 2ax plus bx squared plus 2b plus cx plus d. All of that represents the numerator because I have a common denominator here and now here. Let's group them in a fashionable way. All right, now, there's a lot of things going on here. First, there is no x cubed in this expression. So, I can assume that the a would have to be 0. That's my first equation. I do have a match with the bx squared. So, b equals negative 2. Further, there is no x component in the numerator. So we can say that 2a plus c has to equal 0. Nor is there a constant. So 2b plus d equals 0. This is a system of 4 different equations, but they're relatively easy to solve. A is 0, so therefore c equals 0. B is negative 2, so this is going to lead us to D equals 4. Let's put it all together. We have negative 2x squared over x squared plus 2 squared should be equal to a is 0 and the b is negative 2. Here the c is 0 and the d is 4. There you have it, the partial fraction decomposition. Even though there were no other answers for a and c, they just equal to 0, that's probably because this is a single term in the numerator. If there were more terms, then you might have some more equations to solve. How will this all tie into calculus? That's where we're trying to get to. So we've seen limits a little bit before, but officially, a limit to infinity. The end behavior of a function f of x as x gets greater to positive infinity or lower to negative infinity is given by evaluating the limit as x approaches positive infinity or negative infinity. Let's take a look at a small example Hopefully it will serve as a reminder. Here is the graph of f of x equals 1 over x. So, the limit of 1 over x as x approaches positive infinity. Well, if x is going to be greater towards positive infinity, then what happens is the y value will get closer and closer to 0. The reason why that is if you imagine a very large number for x, say 1 over 1 million, and you put that in the calculator, you're going to get a really small decimal, virtually 0. Now imagine that number getting bigger and bigger, and you get the limit is equal to 0. On the other hand, the limit as x approaches negative infinity, well, we are going to the left. That's where x is negative infinity. You would still get 0. Why is that? Because as x gets more and more to the left, you get closer and closer to y equals 0. So in this particular case, not always, they do equal the same thing. It is the end behavior, what happens to the y value as x goes all the way to the right or all the way to the left, negative infinity, positive infinity. We can use partial fractions to help us evaluate a limit. Example number 5. Evaluate the limit using partial fractions. Okay, first of all, we are used to just plugging in a number and evaluating limits. If I were to do that here, and I plugged in a really, really big number for x, then that second power is going to take over the numerator, and you're going to still get a really big number. It's going to be infinity. And the same thing will happen on the bottom. So this is going to be infinity divided by infinity, which is actually not 1. It doesn't tell us anything about the end behavior of the function. So we can't come to a conclusion there. Therefore, we need to somehow manipulate the function we're going to say manipulate the expression to get a better idea of the end behavior. So what could I do? It looks like I can break up this particular expression into its partial fraction decomposition. So first, recognize that it's improper, and that means we have to perform the division. So negative 5 times 5x squared minus 5x. We should move this over. And we're going to subtract that. Negative 5 minus a negative 5 is going to be 0, so that's good. 0 minus negative 5, that's going to be positive 5x. and then bring down the 2 plus 2. We can't go any further than that. So now this is the remainder. Let's write it out again. So we're going to say this is negative 5 plus 5x plus 2 over x squared plus x. Now let's perform the partial fraction decomposition of what's left over. This is going to be equal to a over x plus b over x plus 1. Make a common denominator. So a times x plus 1. B needs to multiply by x. So then bx. All right. Then the numerator must match up with a x plus bx. If you see the x components, then it must be true that 5 is equal to a plus b, and 2 is equal to a. That's a nice answer right there. Let's plug that in. Three is equal to b. All right. The partial fraction decomposition is going to be, don't forget your whole number. Negative 5 plus 2 over x plus 3 over x plus 1. We're still not finished yet because this is a limit. So now evaluate the limit as x approaches infinity, positive infinity that is, of negative 5 plus 2 over x plus 3 over x plus 1. And do some analysis. It's way easier to see. If I take a really large number, like 1 million, and I plug it in for x, this particular fraction will tend towards 0. The same thing will happen for this fraction. It's just plus 1 more, so that'll tend towards 0. So the limit of this function as x approaches positive infinity will be, what's left over? Negative 5. There you have it, a calculus-based problem. Please be sure to comment on this video in order to earn credit, and then have a nice day.